post-treatment of AOP process. As he discussed in his presentation, one of the photocatalytic oxidation treatment using UV radiation and titanium dioxide photocatalyst was quite successful in degrading the organic chemical. But I will discuss why we need the post-treatment and what is the treatment procedure for the post-treatment processes. Basically, we chose titanium dioxide as a photocatalyst for the following reasons: because it is non-toxic, chemically stable, and high photocatalytic activity. While using photocatalyst TiO2, we adopted in the AOP reactor as a suspension instead of using TiO2 as a fixed material on a ceramic or a concrete or glass plating, which is commonly adopted while using AOP treatment. But we chose to use TiO2 in suspension because we knew that it had some limitation when we adopt as a fixed TiO2 material. But however, when we are using as a suspension TiO2, we have some limitation. It is quite effective for organic destruction, but after organic destruction, the TiO2 remains in suspension and it causes secondary pollution. It is non-reactive, but however, we could not achieve a reusable quality water. So we must adopt a post-treatment for AOP after AOP process. So how we will do? There are 3 stages of post-treatment. First, the treatment process itself, how we will recover after AOP treatment, how we will recover the TiO2, the used TiO2 is the first step, using a simple and effective recovery process that we will analyze. The next stage is after we recover the TiO2, how we can regenerate. I will explain in the next slide why we have to regenerate, but it is essential to regenerate to bring back its original efficiency of TiO2. So we introduced a new regeneration procedure for TiO2. The last step is the reusability of TiO2. I strongly believe and I hope using this treatment, these steps, the recovery, regeneration and reusability with the organic destruction ability of TiO2 in the AOP process, this combined system, I hope and I believe it will form a sustainable, cleaner technology when we adopt this process. So, this is another strong reason why we have to regenerate this TiO2. As you can see here, after the first treatment using the TiO2, the efficiency for 50 ppm of TPA, synthetic water, was around 10 hours, but it grabbed for complete destruction. But when we use the same TiO2 without any regeneration in the second process, we could observe the efficiency was gradually decreasing as we are using the number of times of TiO2. So this suggests that the regeneration, apart from recovery, we must adopt also the regeneration process. Okay, this briefly shows the TiO2 characteristics. The point to be noted is that it's a small nano-sized particle of 21 nanometer, and so it remains in suspension without settling if we do not adopt any recovery process. Okay. This is the recovery process. We have separated into 3 stages. The first stage, this is the AOP treatment of after organic destruction. The TiO2 amount of TiO2 we used is 1 gram per liter, which produces a 4000 NTU of turbidity in the suspension. So we introduce this AOP treated water into the first stage of the hybrid process for the recovery treatment. First stage involves simple pH adjustment for the settling of the TiO2. This pH adjustment is based on the principle that the 0 point charge or the surface neutralization, the charge, it becomes 0 at a certain pH. So we use that phenomena of TiO2 to settle down the TiO2 in the first stage without addition of any coagulant or any chemical. So we by adopting this stage, we were successfully able to settle down almost more than 90% of TiO2 in this stage. And the supernatant liquid was transferred to the next stage, where there are about 5 to 10% of TiO2 particles suspended, and so we introduced a small amount of ferric chloride or any alum or a commonly used coagulant, very small amounts here to settle the remaining TiO2 here. The supernatant liquid is then taken to the membrane, submerged hollow fiber microfiltration membrane system, where the remaining micro-sized particle in the suspension is successfully removed here, and we get the reusable treated water. At the moment, this system is a preliminary and it is a developing system. There exists a commercialized system without this stage at present, using expensive ceramic membrane, directly using from AOP treated water to using membrane system. I will discuss why this stage is superior compared to the conventional system. So, as you can see here, by adopting this two-stage coagulation followed by membrane system, the final treated water can be of reusable quality water. Before the first stage of TiO2 recovery, we adopted, as I said, the pH treatment. We tested the amount of TiO2 that can be settled by just a simple pH adjustment. What we could see, this is the initial turbidity of around 4,000, more than 4,000, average value of 4,000. We could see more than 95% or almost 99% of TiO2 can be settled here. However, this part is not enough when we check the final turbidity, which is of about 150 NTU, which is quite high. So this indicates that another second stage of coagulation treatment is necessary. This stage shows the coagulation effectiveness using this chemical coagulant. This figure shows that in comparison of the two coagulants, ferric chloride is much more superior than aluminum sulfate. However, this reaction was not performed after the second stage. We have also tested directly using AOP treated water using these coagulant. So we had to use much more coagulant to settle the TiO2 particle. But if we adopt the first stage pH treatment and then followed by coagulation, we require only very little amount of coagulant dose. This is for the ferric chloride. The initial turbidity was 150 NTU. After pH adjustment, then the coagulant, if we adopt coagulation using chemical coagulant, we were able to still decrease the final turbidity further. We were able to decrease it further to 65 or 40 NTU. Then we went to the membrane process. When we adopted the final stage of hybrid membrane system, excuse me, at 50 ppm of first stage pH treatment, second stage is using chemical coagulant for different amounts of ferric chloride, followed by this membrane. This is the permeate volume, permeate flux decline. As you can see here, if we are at 50, if we do not adopt any coagulation stage at all, if we take the AOP treated water directly to the membrane system, we can see as we were able to maintain the final turbidity of we were able to separate the titanium dioxide particle, but the fouling was severe. The flux was severely decreased. If we adopt without any coagulant, for just the pH adjustment only, we were still able to decrease the turbidity, but the flux was improved, but it was not very high. But if we adopt two-stage coagulation followed by membrane, at 50 ppm of ferric chloride, we were able to maintain the flux, we will improve the flux, and as well as remove almost all TiO2 particle. This is the SEM image of at different stages of the surface of the membrane. The first two pair shows the surface and the cross section of the membrane, of the clean membrane. As you can see, it's clean. The second stage is without any coagulation, straight directly from AOP water directly into the membrane. You can see almost all TiO2 particles are forming a thick cake layer on top of the membrane surface, which decreases the membrane fouling, which increases the membrane fouling, and this in turn significantly reduces the life of the membrane. But if we use a two-stage coagulation process followed by membrane, we were able to settle all the particle before it reaches the membrane, and as you can see, the cake layer is very thin, and because most of the particles were removed before the membrane process. This increases the permeate flux and as well as the life of the membrane. In terms of particle separation efficiency, as we can see, the average turbidity value of the AOP treated water without organic was around 4000 NTU. The particle size of the aggregate of the TiO2 particles were 0.5 micron. But when we adopt coagulation stage here, we were successfully able to decrease from 4000 NTU to 65 NTU. But at the same time, we were able to increase the particle size from 0.5 to 3.5 because of the aggregation of using the coagulation technique. And with this was very favorable for the membrane system. In one case, we were able to decrease the particle, and the remaining particle were of more bigger size, which were able to be captured by the microporous membrane filter. So as you can see, the final treated permeate water from the hybrid system was the turbidity was less than 0.5, which is of reusable quality, and the particle size was negligible, which suggests that 100% of the TiO2 particles were successfully recovered. The next stage was the regeneration stage. But here is the recovered TiO2. This TiO2 contains TiO2 plus the ferric hydroxide, ferric chloride we added here, or alum, or aluminum sulfate. This TiO2 contains ferric chloride as ferric hydroxide. Ferric chloride changes to ferric hydroxide. So ferric hydroxide precipitate plus the TiO2 settled particle. So we must separate. We could not use directly. If we are using, the efficiency again goes down. So we have to introduce a regeneration stage to separate the ferric hydroxide and the titanium dioxide. We adopted a three-stage. Here I am showing two. However, we will be also using the three types of regeneration process. First is the mild acid washing treatment, which separates which removes the ferric hydroxide state to soluble state, and so it was able to separate the titanium from the ferric iron elements. And the TiO2 was resuspended in the particle. From the precipitate, it was suspended into the particle, into the liquid. When we adopt the complexing, we are also adopted. This is one method of regeneration. The next method was using by complexing agent, simple complexing agents. Excuse me. This is to go to this stage. We first have to convert this complexing agent. When we adopt this complexing agent, was much better for ferrous compounds than to ferric. So we have to introduce another step here to convert the ferrous into ferric by simple boiling and using ascorbic acid or hydroxyamine hydrochloride. We have to convert the ferric into ferrous, which then the complexing agent can capture the ferrous ion metal here. And this is exactly opposite here. The TiO2 particle is settled down here. This comes into suspension, but here the TiO2 particle is settled down, but ion suspension, the complex ion material is suspended in the water, which can be decanted, and so we can get the regenerated TiO2. This regenerated TiO2 can be readily used can be reused in the advanced oxidation process. The preliminary testing shows that this regenerated TiO2 was the efficiency of this system was in comparison to the real new TiO2 particle. So it was very successful. Finally, the conclusion. As I said, the TiO2 recovery, regeneration, reuse process was very successful. And we adopted a simple and an effective two-stage coagulation hybrid process for TiO2 recovery. Coagulation pre-treatment process was essential before the membrane operation. This could also allow simple porous membrane can be adopted here, and it can improve the life of the membrane. We have introduced a new regeneration processes, which we will be studying. But I forgot to mention the third regeneration process using ion exchange resins also. We will be trying it out using chelating agent, chelates 100 and etc. This this system of coagulation hybrid system in combination with it is very easy to combine this system with the AOP process to form a combined hybrid process, for a continuous process of AOP followed by post-treatment system. This research was funded by the Ministry of Commerce and Industry, Korea government. Thank you very much.